I'm excited to have Madan Musuvathi visit us today. He did his undergraduate in IIT Madras, Chennai in India, and then his PhD at Stanford, and then he joined Microsoft Research immediately. Okay. And he's now managing the research in software engineering group at Microsoft Research. This is a large group that does a lot of good things. And Madan is also he's also a partner. They promised they will stop the noise at exactly 2:30, but maybe their clock is not good. It's Eli Biham, so he should have, okay. In any case, he's a partner at Microsoft, which is the elite, the elite employers in Microsoft. They have like 1% of the employees are partners. They get paid accordingly, but okay. and so, but really, to us, I mean, what is important to us, Madan is a world leader in programming languages and operating system. He had many papers in PLDI and OSDI and SOSP. He had also 2 Best Papers Award in SOSP and OSDI, right? Which buys you a job in any academia, I think, maybe. Maybe. And he did, his research focuses on analysis of concurrent systems. He did a lot of, so he did like end-to-end sequential consistency, where, so everybody is unhappy about all these change of order of instructions. So Madan had a project that shows that you don't win so much from all of this, and you could work with sequential consistency. He also did CHET, which brought model checking to the real world and allowed it to work practically. He has lots of work. Maybe he'll survey some of them. But without further ado, let's welcome Madan to the Technion.
Thanks a lot, Aris. So can you hear me okay? Cool. Thanks for the great introduction, Aris. So please, I like having lots of questions during the talk. So please, let's make this interactive. It'll be a lot more, fun. I think I'll get a lot more out of it if there are lots of questions. Today I'm going to be talking about, how programming languages and compilers can help in the world of cryptographic computation. This is some work that I started working a year and a half ago. It was essentially, it started by chance. I happened to give a presentation right before Kim Line. He's a cryptographer, and I thought there was a bug in his slide. And it turned out that it was not a bug. And that meant that there are lots of techniques that we had been working on could be applied in this new domain, and that's how this whole research started. It started by chance, and I'm actually pretty excited about this work. This is joint work with a bunch of people in RISE. RISE stands for Research in Software Engineering at MSR. So RISE and the crypto group at MSR. We also had like 2 interns who contributed a lot to this work, Roshan and Betty. So before I start, I thought I would just give you a background about the RISE group. So we do research, any research related to programming languages, high performance computing, compilers, verification, theorem proving, automated theory, and software engineering. So we build a lot of tools to improve, to find bugs, to improve the productivity of developers. And we also work on making everything programmable. We want to, have kids learn programming. So how do we design new programming languages so that's accessible to non-programmers and so on. So let me talk about cryptographic computations. So in general, there are lots of different applications where you want to evaluate a program as a circuit. And fully homomorphic encryption, secure multi-party computation, zero-knowledge probes. I mean, they're all different cryptographic applications. And it turns out that in all of those cases, having a good compiler that does these domain-specific optimizations can be a huge boon, both in performance and correctness and guaranteeing security. And so this talk is essentially a call out to all the PL people in the audience to start looking at this domain. I think there's lots of new open problems for us to contribute. This talk, I'll mostly be talking about fully homomorphic encryption. That's because that's what I've been working on. But there are other people who have actually built compilers for secure multi-party computation. In secure multi-party computation, what happens is you have some data, I have some data, and then we still want to compute a function on those two values without leaking the information to each other. Zero knowledge proofs are like a separate domain where I did some computation, but I want to prove that I did that computation to you without leaking any information about the data that I did. Like for example, if you tell your bank to update your bank balance, the bank needs to they can use zero knowledge proofs to convince somebody else that they did the bank update correctly without leaking any information about my bank balance. So and I'll also talk about, I'll come to fully homomorphic encryption. In all of those cases, we have a program. That program needs to be compiled into a specific circuit. And the circuit changes in these different applications, but the challenge is to actually evaluate these circuits, generate these circuits that are in such a way so that you maximize performance while guaranteeing security. So yes? So let me just hold on to the question. I'll come to this. So here is the promise of fully homomorphic encryption. So imagine that you have some data. So what you could do is you encrypt the data, and then you upload it to some server. Now, so the nice thing with this is that you don't have to, if the data is sensitive, you don't have to manage the data yourself. You can have somebody like a cloud provider manage the data for you. So you've offloaded your storage. But the nice thing with fully homomorphic encryption is that you can actually do some arbitrary computation on this encrypted data without requiring the key. So that, so what happens is if you actually take this answer and then give it back to the client can use the key to decrypt it to find the answer. And the guarantee provided by FHE is that this is the same answer the client would have had she run this compute in the client. So the promise of FHE is that you've not only offloaded your storage, but you've also offloaded your compute. And so this is imagine that you have a function here, right? So this is evaluating the function here would be the standard way of running the program. And for every such function here, there is a different function, the homomorphic version of that function, that you need to evaluate on the encrypted data to get the encrypted answer. And so, so for every such F, you have to compute a different circuit based on the encryption scheme that you have used. Okay, so that's why you need a separate circuit. So, this is very, very interesting if it works, because the encryption key never leaves the client. So you don't have to trust the server, to make sure that the server does not know anything about your data. So, for example, one way to do it would be to actually give this key to the server and sort of make sure that the server does not leak the key to other people. Right? But you never know what happens in the server. Right? So, the nice thing with this is that you get a really good trust model. You neither have to trust your hardware, like the hardware that the server is running, or the software that the server is running. Okay? And you just have to trust the computation on the client side. And that's the advantage of fully homomorphic encryption. And so this basic idea that such a encryption is possible, I think it was in 1978. There's actually a paper by Ron Drivest et al., which actually showed that all the promise, like all the things that you could do if such a scheme existed. So it's actually a really great paper. If you read that paper today, you can see how real some of the things that they proposed in 1978 has become. They talk about, hey, there are multiple ways of doing it. Maybe you just trust the hardware to, they predicted Intel SGX, like, in 1978. So it's actually a really fun paper to read to see how much forethought that they had in 1978. Right. So, I mean, that paper actually said, like, hey, it'd be nice if we had such an encryption scheme where you can do arbitrary computation on encrypted data without requiring the decryption key. And it took a long time before they actually showed that such an encryption scheme is possible. So it turns out that many encryption schemes are partially homomorphic. So you can either do addition, or you could do multiplication, but not both. And so Gentry was the first person to propose a scheme where you could do both addition. Actually, you could do both ANDs and XORs. And so that once you have the two operations, now you can evaluate an arbitrary circuit. And this scheme, when it was proposed in 2009, was a theoretical breakthrough. But I think there was it was understood that it was not practically feasible because the overhead of implementing that scheme was very, very large. Okay. But since then, there's been lots of cryptographic innovations where people have proposed better and better schemes which are more practical. I think the first, in 2012, so before 2012, all the encryption schemes were operating on Boolean, like on bits. So in the sense, on Boolean circuits. And in 2012, we had integer schemes where you can actually do addition and multiplications on integers. So you can actually take, rather than taking an arithmetic circuit and then doing bit blasting, converting into bits, this is more efficient now because you don't have to build these Boolean circuits. And in 2016, so in the sense, just recently, like 3 years ago, there was a scheme called CKKS where you can do fixed point arithmetic. So here you can only do integer operations. Now we can actually do fixed point computations. Once you can do fixed points, some new domains open up. Now we can do like machine learning and things like that. So in fixed point is essentially you can you can do real you can do approximate real numbers. It's like it's rational numbers with some precision, right? So essentially what you could do is that you can say, can I? Yeah. So essentially it's in floating point you can change the precision, right? In fixed precision you can just say some integer dot some sort of bits in the decimal point. Okay? So you can emulate it, right? So I'll actually, yes, that's a good point, right? So in the sense you could, you can use rationals to, you can use the integer schemes to sort of encode your rationals. And it turns out that there's one particular operation you need to make it more efficient. So I'll actually explain to that. That's a good point. Right? So anyway, so the point here of this slide is that this field is moving really fast. It's a very it's recent innovations. Like all of this is happening within a decade. And then if you actually plot the performance of these schemes, where this is where in 2009, as you plot what happens. So this y-axis shows the overhead of doing an operation in homomorphically versus the cost of doing that operation on unencrypted data. And so initial schemes were like 12 orders of magnitude, and right now, this is right now we are at around 4 orders of magnitude. So this includes both better and better encryption schemes and better implementations of those encryption schemes. So there have been people have been like building better, more efficient libraries.
Different computations have vastly different overhead and computation. Shallow computations can be done much more efficiently.
So this is, I think, this is a cost of a single multiplication.
With arbitrary depth, so it can do iterated multiplications over and over, and this is the overhead.
No, no, no. This is for one particular application. I'm not evaluating circuits. So this is the cost of doing a single multiplication.
With bootstrapping, so without.
No, this is without the cost of bootstrapping. So yes.
For general computations, you need the bootstrap.
Yes, yes, yes. Agreed. Agreed. I completely agree. Right. So again, this is just to again to show that things are improving, and I just wanted to show where the where the overhead is. Right. And so and the interesting thing is if you actually plot Moore's law would look something like this. Right. So this is y-axis is logarithmic. So so I'm just saying that this field is rapidly improvement, even though you still have like 4 orders of magnitude of overhead. Right? So the way I like to call it, like so rather than saying FHE is becoming practical, you can say it's an edge of practicality. Right?
By the way, this is super fast, and this is only for very simple computations. If you want to emulate general computations, the overhead will be much bigger than 10 to the 4.
Yeah. Agreed. I completely agree. Right? Yeah. So yeah, I'll get to that. Right. But the hope here is that from a systems like for somebody like me who cares about building real applications, I think there's lots of interesting work that still needs to happen. For example, I'm going to say, hey, the cryptographic community is going to come up with better and better encryption schemes which are more efficient. But the point here is that it's time for other people to start contributing to this world as well. Like it's in the sense, one of the things that I will show in this talk is that better compilers can actually give you orders of magnitude improvement as well, right? Yeah. So is there a question?
No, it's just about clarity on the type of computations we supply, because I'm 10 to the 4 great, and just wondering which types of computations we supply. So what kind of computation with big data can we do with this?
Okay, so that's a very good question. So in the sense, you're still very far away from taking, let's say, building a database, right, where you have gigabytes of data, encrypted data, and doing arbitrary SQL. I completely agree. Right? But the interesting thing is not figuring out what you cannot do, but to see what you can do and if there is some interesting use for it. Right? So there are certain problems that you want to solve from a research point of view, and you want to be like 5 to 10 years ahead of the startups, which are going to make it more practical. I think this is a good time for researchers to start thinking about this problem, so that 5 years from now, there'll be startups who can actually build these like big applications. Right? There's still lots of challenges that need to be solved. Like so I think one thing that you've been like pointing out is that the way these FHE computation works is that there is a hard limit on the depth of the circuit that you can evaluate. And so you cannot run a Turing machine for arbitrary depths. And so so there is actually something called the bootstrapping operation that you need to perform before you run out of this, like the depth budget. And that bootstrapping operation is very expensive. But hopefully what I'll try to convince you is like within that limit, there are interesting things you can do. So, before even consider all of these other problems that we've been talking about, it turns out that programming is still a hard problem. because it looks very much like low-level assembly programming. So what you have are these FHE libraries. So think of them as implementations of these encryption schemes that will tell you, here's how you encrypt your data, and you have some encrypted versions of A and B. You can call a function to do A plus B, and you can call another function to do A times B. Right? And apart from this, there are lots of little minor details you have to get things correct in order to make sure your programs are correct. And so these libraries could be implemented on your CPU or GPU or FPGA. Like, this is where you get your performance. But this talk is going to be more about, how do you write these programs? And currently, even writing these programs using these libraries require lots of cryptographic expertise. And this is where we are hoping that, that with better abstractions, you can solve all of these problems. So I'll actually talk about some of the challenges. So as we said, it's still really slow. A single multiplication on like the state-of-the-art encryption schemes takes 50 milliseconds. Okay? But interestingly, these schemes support very large SIMD vector bits. So you can actually do what is called batching. So rather than doing, so imagine that you have, 16, let's say you want to perform 16,000 multiplication. So what you could do is encode all these 16,000 integers into a big integer, and then you do a single multiplication on that big integer that corresponds to doing point-wise multiplication on these individual integers. Right? And so this is something, if you think about what happens in the hardware today, we have these vector instructions that can do 128 or 256 multiplications in parallel in a single instruction. The only difference is that the vector widths are much larger. So imagine that you're building a vectorizing compiler. The kind of things that you have to reason about to fill up these large vector widths is a challenge. And so if you have enough parallelism in your application, and if your application or the programmer is good enough that you can utilize the SIMD capabilities of these encryption schemes, then interestingly you can operate at at microsecond, you can do a multiplication at microseconds. And so the nice reference point is this was the speed of the original 8086 microprocessor. If you compare those 8086 processors to the processors today, they are extremely slow, but you can still build, you could build interesting applications with those old processors, right? And so, and this is where I mean, it is beginning to become practical, right? It's interesting for us to start thinking about it, okay? And there's lots of trade-offs, even even if you forget about all this restrictions. There are lots of trade-offs that you have to do things correctly in order to get correctness and security, and then managing the sizes of these encrypted messages in order to get performance. Yes?
So you said one multiplication translates to the 16K multiplications a year. Can you say what is the nature of that? It's what, it's some ideal lattice multiplication thing? What's that operation in terms of?
So the encryption schemes, they let you do batching. So you can take multiple integers and create a vector of these integers and then encrypt them. So think about you can create a vector of integers and then create a single ciphertext that encrypts all of those vectors. Then you can take two such vectors, encrypt them, and then do a multiplication operation on the ciphertext that corresponds to doing individual multiplications, doing point-wise multiplication of the two vectors. So this is sort of the programming abstraction these encryption schemes provide.
Suppose I only care about one multiplication.
Yes.
The 2 bits. I just want one multiplication.
Yes.
I'm still taking 50 milliseconds.
Yes.
What am I paying for these 50 milliseconds? What is the processor doing? So I'm not interested in batching. I'm just asking.
What's happening under the hood?
Yeah.
Polynomial multiplication.
So under the hood, there's a polynomial multiplication. Thank you. right? So I'm not repeating the question. Is that okay? Yeah. Okay. Yeah. So
It's one more polynomial constitution?
yes.
Is
So
it what, in a, like a ring or is it
okay. Yes. It is in a. It's in a crazy ring. Yes, a big ring. So I'll actually I'll try to get more details. Right. Okay. Pardon? So, so one of the things, as we were talking about bootstrapping, so the reason is that the way these encryption schemes work, they add noise to your message in order to encrypt them, and this noise grows as you do operations. And so imagine that you have you have A and B, you have encrypted versions of A and B. There is some noise, and when you want to compute A times B, the noise grows with the maximum of noise of A and B and some constant. Right? And if you think of this as rounding error, that's what in normal unencrypted versions you have rounding error. Right? So usually you don't get this max. Right? So usually it's it's a sum of the rounding errors on both sides and so on. And so one nice thing with the max is that so you don't care about the number of multiplications that you're doing. You only care about the depth of the circuit, right? And so what that means is that imagine that you have some computation that looks like this. Instead, if you actually, rather than doing computation sequentially like this, if you did it in a logarithmic fashion, in a more parallel version, right? So you're actually reducing the depth of the circuit. And so the noise growth here is much better here than with this. Right? And so this is one of the reasons why I got interested in this problem, because I was interested in taking computations that look sequential and then changing it such a way that you can execute it in parallel. And so one particularly, for instance, we were looking at stochastic gradient descent. You want to do machine learning. It is a sequential process of because you're at every step you're updating your parameters of the model, and the computation would look like this. And so what we could do was to actually come up with a parallel version of SGD, where your computation would look like this and guarantee that the output is the same as what you would get if you run it sequentially. And so what that meant is that, so if you look at these encryption schemes today, I think the depth is roughly for reasonably, for acceptable parameters, the depth is around 20. Right? So you can only evaluate circuits of multiplicative depth 20 before you need what is called the bootstrapping operation. And so if you're imagine you're doing ML training, you can do SGD, you can only do 20 updates to your model before you needed a bootstrapping step. Now, if you parallelize it, then you can essentially do 2 to the 20, right? So 1 million updates to your model. And so there's a huge opportunity to sort of take sequential circuits and then parallelize them and then actually have a huge performance improvements in this setting. And so what happens in bootstrapping is actually very interesting. So what you're doing is literally taking the message, decrypting it, and then encrypting it back. But you're doing the decryption and the encryption function homomorphically. So it's so that's actually a neat idea. So depending on the encryption scheme, the circuit that you have to generate in order to decrypt and re-encrypt can be very complicated. And so people have been, there are some encryption schemes that have more efficient bootstrapping operations. And again, that's all interesting research that cryptographers are doing. So so in general, there's this challenge of making sure that your circuit that you're evaluating fits within the parameters of the model. Okay. So what we ended up doing, so what we were interested in is just taking two particular encryption schemes called Hyan and Seal. So Seal is an open source encryption scheme from the crypto group at MSR. And Hyan is the first encryption scheme that did fixed point arithmetic. And so right now, even Seal supports the fixed point encryption scheme. And so what we did was we built a runtime and a compiler. And what we wanted to do was to take tensor programs. So the one particular application that we were motivated by is to do neural network inference. So imagine that you have medical data, like patient images, like, let's say MRI images of your brain or your liver. You could sort of encrypt it, and then you can run neural network models. You can do inference on that to find out whether your patient has like a disease. Right? And you could do that without decrypting it. So that way you're protecting your patient's privacy. So that was sort of our motivating application. And we wanted to see if you could take those tensor programs and then see how much performance improvement you could get. So, so this stack looks very much like the unencrypted ML inference stack. So essentially, if you think of this layer here as your hardware, so what you have, so we built like our runtime corresponds to Intel MKL. So these are the libraries that provide custom implementations of these tensor kernels, like matrix multiplication and all the linear algebra operations. And your compiler corresponds, it sort of builds on top of these libraries to do additional optimizations, and so that you're raising the programming abstraction, so that at this point what you're doing is very much like doing TensorFlow or PyTorch programming. You're just dealing with tensors and doing operations on your tensors. So this is sort of just to front load the results. So these are some of the neural networks that we could evaluate with a compiler. So SqueezeNet is, I think, around 20 layers, neural network layers. I think it's the largest neural network that could be homomorphically evaluated when we publish the paper.
How many nodes?
Pardon? How many?
Nodes.
What do you mean by nodes?
Nodes.
Number of neurons. So we only care about the depth of the circuit, right? So the depth was like multiplicative depth was around 20. I don't remember. I think it's like hundreds. I think the input images is around like 700 pixels.
What we do internally, you approximate it per square?
We approximated with polynomials.
So what's the effect in the accuracy?
Oh, good questions. So you probably thought about this a lot. So yeah. So so here's what we did. So what you do is you take your network, and I actually had a slide on this, but much later. So what you do is you take your network and then train it with ReLUs, and then you replace your ReLUs with a quadratic, like ax squared plus bx plus c. Interesting thing is that you retrain the network with A, B, and C being your the new weights, while you're keeping the other weights constant. And so when you retrain it, then you can actually improve accuracy. So so I don't remember, again, I need to look at the paper. So there is a reduction in accuracy, right? So it doesn't come for free. So we're actually looking at, we're doing some follow-up work on that, where we can actually now, if your network satisfies certain properties, then you can provide error bounds. So people have done some work on robustness properties, right? In the sense, like, it's a small delta in the input does not create huge deltas in the output. We can sort of repurpose that analysis to prove that the error that you're adding by changing your ReLUs to a polynomial, you can sort of bound that error. So you could, we can provably say that the accuracy will not reduce by more than this amount. The interesting thing there was that with every layer, you had to come up with different polynomial approximations that captures the distribution of points that are coming to the ReLU at that layer. So if you're a little bit careful, you can sort of minimize the resulting accuracy, right? So one of the restrictions of FHE is that you can only do addition and multiplication. So what that means is you can only evaluate polynomials. So you can still do like a lot of nonlinear stuff, but just polynomials. And not all of machine learning is just polynomials. And it turns out that if you take your activations and you say, I'm going to retrain a network with polynomial activations, it doesn't work well because polynomials don't behave properly. And like training becomes very messy. It doesn't work empirically. That's the only thing I can show. So you have to be really careful in how do you replace your ReLUs with polynomials and so on. But so, yeah, go ahead.
Another question, so if you look at alternative approaches that don't achieve the same model of trust, let's say in the NPC, we have the rough ballpark estimation that you can select 165 seconds. If you do it in the setting of 3 parties, 1 corrected party, what would be the response?
What is okay, so the kind of optimizations we're doing are very specific to FHE. Right? So there's been lots of work on how do you do MPC style optimizations. So the nice thing with MPC is that you can evaluate ReLUs. But it's more expensive.
You can mix also.
Yeah, yeah.
Let's do this in the end. We ask for it to be interactive.
Sure. Yeah, that's okay.
If you want it to stop being interactive, okay.
No. That's okay. That's okay. That's okay. Okay.
Maybe the rest of the audience doesn't
okay.
is
Yeah.
not controlling the material.
Okay.
Well,
Sure. Okay. Okay. So there are okay. So yeah. So there are other. I mean, so the optimizations that I'm doing do not correspond to the optimizations that you want to do in secure MPC. Okay. Okay. So anyway, so the important thing I wanted to show was that. So this is the default. So imagine that I gave the encryption library to you, and then I wanted you to implement a neural network. The normal thing that you would do is like even the simplest like the simplest neural network, your inference latency would be around 922 seconds. Now you sit with a cryptographic expert, and then sort of like pick their brains. You can reduce it to 140 seconds. So this is just showing during the length of an internship, what a compiler could do, right? So our first version of the compiler was actually faster than what the expert could do. And when we implemented more and more optimizations, you can see the reduction in the performance. So this is just to show that compilers can make a huge difference in your application. Okay. And this is actually the industrial network was. We have a collaboration with a startup that is interested in doing medical imaging homomorphically. And so I think they were not even able to run it homomorphically, and so now we can actually do inference at 56 seconds, which is, it's not fast, but it's acceptable. So, so now I'm actually going to deal in the details on some of the optimizations. So how much time do I have?
10 minutes.
Ooh, okay.
Madan?
Yes.
In the previous slide, during the improvement of the running time, was a increase of accuracy?
No. So essentially they are, so once you replace your network with the polynomials, so these are all semantically equivalent. Right? So at this point, these optimizations, we're not playing all the ML tricks. So once you give me a circuit, it's semantically the same. Okay. So so now just to go one level deep as to what happens in these encryption schemes is that you're taking your input, which is like a vector of inputs, vector of integers, and then you're creating a large polynomial. And all your homomorphic operations correspond to operations on this polynomial. And there are 2 important parameters called the n, the degree of the polynomial, and q, which is the modulus of the coefficients. So each of these coefficients are modulo some very large prime q. And so these are the encryption parameters that you need to set. And so what happens is that based on the depth, given, let's say you want, given a circuit, based on the depth of the circuit, we talked about the noise growth, your Q has to be large enough so that you can evaluate that circuit correctly. So in theory, like you can take an arbitrarily large circuit, and if you don't care about performance, you can set Q to be really large so that you don't need the bootstrapping operation at all. But you cannot do it because you will lose performance. And given a Q, you have to pick your N such that you're doing the encryption is secure. So if your N happens to be small enough, then it turns out that you can break the encryption. Right? So what you want is you want to operate in this region where you're both correct and secure, and you want to make sure that N and Q is as small as possible, so that you maximize performance while you're correct and secure. And one of the things that the compiler can do is actually explore this space to find out the best N and Q, and we were able to do it better than what an expert can do. And if you think about it, this is one place where the compiler, by doing more systematic search, can beat human beings, like we can beat experts. Okay. And so coming back to the fixed point, so the way you do fixed point arithmetic is to sort of, you represent 1.1 as 11 by 10. Right? And so the problem is that if you, every time you do the operation, your scale, the denominator increases. Right? And so for example, you had two numbers with scale 10, and now you get a number with scale 100. And so what that means is when you do multiplication, your scale is going to grow. And it turns out that very soon you start having overflows in your overflows in your coefficients, and so the scale cannot grow to a large amount. Right? And the innovation in this encryption scheme CKKS in 2016 was, any questions? Okay, thank you. Right. Was that they let you do what is called the rescale operation. So you can sort of take 242 divided by 100, and you can change it to 24 divided by 10. Right? So you can essentially, not only could you do addition and multiplication, now you can divide by some constants. So that itself, that was the key innovation that you needed in order to do fixed point very efficiently. Okay. And what happens is that whenever you do the rescale operation, they consume Q. So your Q sort of, you lose some modulus. And so this is essentially what we do, is that given a circuit, we sort of know what the Q should be, and then you pick the N such that you get 128-bit security. Right?
Can you roughly say what are good values for Q and N for let's say that 56-second computation that you said? Like how big are they roughly? The degree of the monty?
Sorry, I don't know. I don't remember. A compiler is picking it up. That's the reason why you need to have a compiler, so that you don't have to worry about N and Q. Makes sense, right?
No, but like this Q in kilobytes or bytes? Or
Oh, that's what you mean. Like thousands. They're roughly in the thousands.
thousands of bits.
No. Q is.
The modulus is not like each integer or whatever it is. It's in the range of thousands of bits. Or
Thousands of bits. Yeah, you're using big integers. Yeah. So it turns out that there are some schemes where what you could do is you can use Chinese reminder theorem to represent this big integer with lots of machine integers. But all of that is happening below the encryption scheme. That's a nice thing because I don't have to worry about it. So it's exposed in a different way, in a pesky way, the interface. That's another reason why you need to have a compiler, because you don't have to worry about it. So again, so for enough time, so there are other, so when you're multiplying, you want to make sure that the modulus is the same, because the modulus keeps changing. As in when you do the rescale operations, when you're doing the additions, you want to make sure the scale is the same. Again, because if you want to take 2 by 10 and add it to 3 by 100, you have to change 2 by 10 to 20 by 100 so that you can add, right? So again, doing this manually by a programmer, this is better done by a compiler. And so I'll skip this about approximations. So in general, lots of pesky little details are better done with the compiler. And that's what we did. And so in fact, from a compiler perspective, these are all very straightforward. But that is the point, is that things which are simple for us from the compiler world can make a huge difference in the crypto world. Okay. So another thing is that, we talked about these vectors of integers. And the size of this vector is actually determined by n. Okay? And so what you could do is sort of take this bunch of integers, encode them into a vector, and then you encrypt it. And so imagine that you want to do a circuit. You build a circuit, assuming a particular size of the vector width. You pick a q, and then you pick an n based on the q. And the n will actually determine the vector sizes. So let's say the vector size is increased, then what you could do is you can actually re-implement the circuit to actually make use of this larger vector widths carefully. So that is going to change the circuit. So it's actually not a single process. It's an iterative process the compiler does. Picks a q, picks an n changes the circuit. For that circuit, it picks the q and an n and so on. So it's an iterative process till it converges. Again, that's something that's easy for the compiler to do. It's very difficult for the human to build such circuits. So we stop when we converge, right? So whether it's optimal or not, I don't know. Okay. So just want to tell you about, so there are only certain operations that you can do on these vectors. For example, you can do pointwise operations, and you can also do rotation operations. And interestingly, these are the only two operations you can do. Right? So if you want, for example, if you have a vector and you want to randomly, pick one value out of this vector, the only way to do it is to, rotate it, bring it to the top, and then mask all other things out. Okay? So in some sense, if you're familiar with SIMD programming, certain operations that you do are fast, and certain operations are very expensive in the homomorphic encryption world. Right? And so things which are obvious, like let's say matrix multiplication, you have to do it in a very special way when you want to do it homomorphically. So imagine that you have two simple 2x2 matrices. In fact, it turns out that you do a layout. So the way you encode this matrix is in this special way, and I'll explain why. And you encode B in this particular layout. The advantage is that if you rotate B and then you add, you've actually replicated the values this way, and you can rotate by 1 and then add. You would replicate it that way. The advantage is that now in a single multiplication, you sort of got all the 8 multiplicants that you wanted to do the matrix multiplication. Okay? And so now you take this vector, you rotate it again, you add it, you get the 4 values that you need for the matrix multiplication, but you also have some junk values that you mask it, right? And so this is how you would do a 2x2 matrix very efficiently. The interesting thing is that you started with 2 matrices in this layout, and you got a resulting matrix in a completely different layout. Right? And so now what you could do is that you can write a library that says, oh, I'm always going to take matrices in this format, and then whenever I want to multiply, I sort of convert this to this layout and take the result from this layout to the standard layout. But again, every such layout transformation is expensive. So instead, what we do is that we actually emit different code. Like if you want to multiply matrices of this and this, we actually have a different way to do matrix multiplication. So the layout of the variable of the matrices changes throughout the circuit. Again, something that's very easy for the compiler to handle, very difficult if you are actually doing this manually. Okay. And so this is for a simple matrix multiplication, but then what you need to do is in machine learning, you're dealing with tensors. And so the kind of layout transformations you do for these tensors is a lot more complicated. And so I'll skip the details. Essentially what you do is that the layout transformation becomes a lot more complicated. There's a huge state space. So we sort of, we got an asymptotic complexity of these different operations from our crypto friends. And then we did micro benchmarking to actually determine the constants for this asymptotic complexity. And that was our performance model. And based on that performance model, we can sort of search the state space to find the layout that works the best. And that, that essentially all the optimizations that we had to do to get the performance improvements. Okay? And so this is just a graph to show that we are able to, we get much better performance than handwritten models. And in fact, there are 2 networks that we don't even have a handwritten model because they were just too, very difficult to manually write those models. And also interestingly, the best layout depends both on the encryption scheme that you're using and the network that you are encoding, right? So, this is one of the reasons why you need an auto-tuner. Okay?
Using a different encryption scheme can change the accuracy of the network after you turn it into FPGA, right?
No. So essentially, okay. So once you have a circuit, the compiler makes sure that you get semantically the same output. Okay. And so irrespective of the encryption schemes, the different encryption schemes have different parameters that are optimal. One issue is that the CKKS adds noise. So that noise can creep in your evaluation. But one of the things that I skipped was that we ensure that the way we choose those parameters, the noise does not affect the final semantics. Right?
So you
yes.
have like picking parameters differently for seal and for here.
Yes, exactly. We needed that. Okay? And so there's still some follow work that we're doing on doing this the noise cancellation, whatever, making sure that you get the same output for a noise. We can do much better. So currently we're doing it ad hoc way, but I think if you have better noise modeling, the compiler can do a better job in picking those parameters. Okay, that's our hope. Yes? So your cost model will change on how the encryptions. So essentially, our abstraction is that the encryption layer provides us addition and multiplication, and the implementation of those 2 operations changes whether you're running the encryption scheme on the CPU or a GPU or an FPGA. And so based on that, your cost model will change. So the asymptotic complexity will remain the same, but the constants that you're using in your asymptotic complexity will change, and based on that. So the data layout should not, that's what I'm saying, right? So in the sense, the data layout depends on the performance model. The constants in the performance model will change, and so maybe the compiler will pick a different data layout. Right? So you could potentially change. So skip this, essentially saying that there are tons and tons of optimizations that you can do. So one of the things that we are trying to do is to actually generalize our work to not just do neural network inference, but also do arbitrary vector programming. So right now we have like a Python interface in which you can manipulate vectors, and then a lot of the details of homomorphic encryption are just sort of taken by the compiler. So I just wanted to show where we are. So imagine that you're doing some image processing where, I think this Harris corner detection, where you have an input, and this is the unencrypted result. And this is what we get when we do it homomorphically. And so this is sort of the program that you'd have to write today in order to evaluate this homomorphically. And so again, I already showed you how we can actually pick these NNQ automatically. So we don't need that. And then we can do this. We can do the scaling, based on the accuracy that you have. So you don't have to do that. And then again, so these are all the rescaling that figuring out where to insert the rescaling correctly actually changes performance. Again, the compiler does it automatically. Pardon? Okay. And then, again, so nice thing is that we can have the compiler encode some of the knowledge from research papers so that, you know, we can eliminate that as well. And then, I mean, this corresponds to, like, you know, this is a convolution. And if you had like a fast implementation of convolution homomorphically corresponding to Intel MKL and so on, you can call those libraries. And this is where you're approximating, doing all this to approximate a square root. And so what we are doing right now is to sort of having an approximate library that can approximate these you know, non-polynomial functions with appropriate polynomials. And so this is how, like, you start with the program. This is how it looks today. Okay. So to conclude, I'm going to claim that, you know, cryptographic computation is a systems problem and a PL problem. And so a lot of things that we can do to help, you know, make cryptographic computations more practical. So in general, in some of the communities that I have talked to, whenever I say I'm working on homomorphic encryption, they start laughing, saying that, oh, homomorphic encryption is completely impractical. Why are you wasting your life? Yeah, it's still impractical, but I think it's at a point where it's becoming interesting for us to start looking into it. And there are still lots of PL challenges that are open for us to contribute to. So, I'll be happy to take more questions.